Hello class, we're about to start section 2-3, and in our syllabus we have the page numbers. We have page 133 and page 141 are the pages we're going to do on section 2-3. Now, we start on page 133 and it's lesson 2-3, warning graphic content. Our learning objectives are to understand and use a rectangular coordinate system, connect data to graphs and interpret graphs, define slope as a constant rate of change, define and interpret the y-intercept of a line, and write an equation of a line that models data from a description, table, or graph. Okay, now we go to the bottom of the page. If you've been paying attention to the news at all for the last several years, you know that the unemployment rate in the United States has been a big story. But what did unemployment look like before the economic crisis of the late 2000s? These tables display the average annual unemployment rate for the years from 1992 to 2011. Number 1, use the table to write a verbal description of trends in the unemployment rate over that 20-year period. Now, if we look here at this 20-year period, if you look from 1992 to 2000, the rate was decreasing. It was a steady decrease. So we could write the rate decreased from 1992 to 2000. And then we look from 2000 to 2003, the rate increased. So it increased from 2000 to 2003. Now if we look here from 2003 to 2007, it decreased again. So it decreased from 2003 to 2007. And then from 2007 to 2010, if you notice, it increased again. So we will put increased from 2007 to 2010. And then finally you notice that it did drop, then dropped in 2011. It says, with enough effort, you were probably able to write a reasonable description, but because there's so much data in the table, spotting the trends isn't exactly a simple thing to do. Next, let's look at the same data displayed in graphical form. Okay, now on page 134, we're looking at the graphical form here. So, in seeing this, you notice here that it went down, went up, went down, went up, and now it went down. Basically what we described in the previous problem. So it says here, when I look at this graph, two things occur to me. It's a lot easier to see the trends than it was from looking at the table. And the graph looks a whole lot like a dinosaur, which is totally irrelevant but still pretty cool. Use the graph to write a verbal description of trends in the unemployment rate, then explain why the graph makes it easier than the table did. So basically, we can put a steady decrease, which we can see here from 1992 to 2000. And then you notice there's an increase from 2000 to 2003. Then a decrease from 2003 to about 2007. and another increase from 2007 to 2010, then a decrease in 2011. The graph makes it easier to see trends at a glance without sifting through numbers. Okay, now it says without the numbers running along the bottom side of the graph and down the left side, we wouldn't be able to understand any of the information the graph provides. Those numbers provide the scale for the graph, and they're always crucial in drawing a graph. Each of the number lines that we write the scale on is called an axis, the plural of the word axis. In preliminary numbers released in early 2013, the average unemployment rate for 2012 was listed as 8.1%. We can add that piece of information to the graph by finding 2012 on the horizontal axis and 8.1 on the vertical axis. Then drawing imaginary lines up from 2012 and right from 8.1 until the lines meet. That's where we put the point corresponding to 2012 and 8.1%, which we show here. So basically, we will connect these. All right, so now we move on to page 135. Notice that when we found a location to indicate that the unemployment rate was 8.1% in 2012, the imaginary lines we drew form a rectangle with two axes. That's why we call this system of graphing a rectangular coordinate system. Each of the numbers we use to locate that point are called coordinates. The horizontal axis is usually called the x-axis, and the vertical axis is usually called the y-axis. The point where the two axes meet is called the origin. Since we didn't need to worry about negative years or negative unemployment rates, the graph we drew earlier only showed positive values along each axis. But there are plenty of examples of data where negative values make perfect sense. So a rectangular coordinate system is often set up like this. As you all can see here, it's a basic coordinate plane. Okay, the process of locating information on a rectangular coordinate system like the 8.1% unemployment rate in 2012 is called plotting points. We identify locations by writing the two coordinates together inside parentheses like this, 2012, 8.1. What are the coordinates of the origin in the rectangular coordinate system above? Now listen, I'm going to go through the origin, and that's where the x and y axis meets, which is here. The origin coordinate is 0, 0. So we will write 0, 0. Now, I want to talk to you about the characteristics of the x-axis and also the y-axis. Now, when you have a coordinate which has an x and a y value, you need to know how the x and a y moves. Now, first thing you need to know, when you plot your point, is always where the y value stops. So wherever the y value stops at, that is where you plot your point. So the characteristics of x. Are these here. Is 1, move right, or 2, Now X doesn't do all of these, it's an OR. It's OR, move left, or stay put. Those are the three characteristics of X. Now the characteristics of Y. The same as X, it's an OR situation. Move up or upward, or move down or downward, or stay put. Now, in talking about these characteristics, for the characteristics of X, if you move right, that means that X is positive. You may want to write that out. If you move right on the X-axis, that means that X was positive. If you move left on the X-axis, that means X was negative. Or if you stay put, that means X was equal to 0. Okay, so now with the Y values, if you move upward, that means Y was positive. If you move downward, Y was negative. And if you stay put, that means Y was 0. And whenever you plot a point, you always go back to the origin. Once you plot a point, you always got to go back to the origin. Now, let's look at number 4. It says, look carefully at the numbers on each axis. What distance does each box on the grid represent along the x-axis? What about the y-axis? These distances are known as the scale for each axis and are always carefully chosen so that all of the points fit nicely into the space provided. Choosing a reasonable scale is the first step in drawing any graph. Now, if we look here on the x-axis, we go 1, 2, 3, 4, 5 places before we get from 0 to 20. So basically, we would end up, if we divide this by 5 according to the spaces we have here, that would break down to 4 each. So this would be 4, 8, 12, 16 up to 20. So the x-axis counts by 4. Now if we look at the y-axis, we go from the origin 1, 2, 3, 4, 5 places up. So 50 divided by 5 is 10. So each one of these are 10. So 10, 20, 30, and 40. So the y-axis counts by 10. Okay, number 5. It said plot each of the following points on the rectangular coordinate system above. Label the coordinates of each point. Okay, now they wanted us to plot these points on a graph that was given to us above, and I kind of marked all over it, but we could still use it. Okay, A is 16, 0. So we start here at the origin, and we go to 16, which is on the x-axis, because x always is plotted first. And since y is 0, we will plot here. So that is our A. Okay, B, we have 0, negative 10. We start at the origin. And remember, everything is going by 10s on the y-axis. And since it's negative, we will go down here, and that's negative 10. Now, if you want to mark these, you could put the ordered pairs by these points if you so choose. So now, the next values, negative 8, negative 20. So we go here to the left, be negative 4, negative 8. So now we're at negative 8, and then we have to go down to negative 20, which is here. Now, last but not least, we have 12, 35. We go back to the origin. We will go to 12, which is here on the x-axis, and we need to go to 35. Remember, all these are going by 10, so 35 is in between 30 and 40. Now, typically, a lot of times when you're first starting to learn how to graph, when you have your points, they typically will put the value in a parentheses. Like this was 1235. Or I should say they put the coordinate by the point. This would be 16, 0. This here would be 0, negative 10. And finally, this one here would be negative 8, comma, negative 20. and we're done. Okay, now we move on to page 136. It says, being able to understand the connection between a graph and the information that it illustrates is not just the most important skill in graphing. Okay? It's the reason that graphing was developed. If you can't interpret the meaning of a graph, it's just really bad art. A small plane takes off from a regional airport. Its altitude at various times is recorded in the table below. Write ordered pairs of the form flight time and altitude for each of the pair of values, then plot the points on the graph. So flight time goes first, altitude goes second. So this will be 0, 0, 10, 4,000, 20, 3,000, 30, 2,000, 40, 2,000, 50, 1,000, and 60, 0. Okay, now we want to plot this here. Now, the flight time in minutes, this is basically number of minutes since takeoff. And then down the side is the altitude. It'll be of the plane. All right, so now we want to graph this. Okay, now these 2 points here are always your zeros for your x-axis and your y-axis. Now we want to graph this. First point we have is 0, 0. At the 10 mark, we go up to 4,000. 20, we go to 3,000. 30, we go to 2,000. 40 is 2,000. 50 is 1,000. And 60 is 0. Now, when we graph this, do a quick graph connecting these points. Now, number 7, I basically did number 7, but it says connect the points you plotted to draw a graph and describe what that graph illustrates. Then add a verbal label to each axis that describes the information it represented. We actually basically did that already when I did the number of minutes since takeoff and then the altitude of the plane and connecting the points. So all we need to do now is just write the statement. The graph illustrates the altitude of the plane in feet based on the number of minutes since the flight began. Okay, now we move on to problem number 8 on page 137. All right, for questions 8 through 13, explain how you got your answer using both the table and the graph. The point is to make sure you focus on the connection between the information in the table and the height of points on the graph. Okay, so now it says, what was the highest altitude reached by the plane? Is the answer based on your graph different? Why? The highest altitude reached by the plane was 4,000 feet. And then when they ask you, is your answer based on a graph different? Both agree that 4,000 feet is the highest altitude. How long after the flight began did the plane reach its highest altitude? That would be 10 minutes. Because remember, the ordered pair was 10, 4,000, and then on the graph it was at x-axis was 10, y-axis was 4,000. So it was 10 minutes, and this is the time that corresponds to the graph and the table. Now they ask, what was the plane flying level? Now, when the plane was flying level, that means it basically stayed at the same altitude. It was 30 to 40 minutes. The altitude was the same at 2,000 feet. How long did the flight last? Flight lasted 60 minutes. When the altitude reached 0 after takeoff, is the end of the flight. Okay, now move on to number 12. When was the altitude of the plane increasing? It increased from 0 to 10 minutes. It went from 0 to 4,000 feet, and every other instance it went down or stayed the same. Okay, now we move on to the next page, to problem 13. It says, when was the altitude of the plane decreasing? It decreased from 10 to 30 minutes. And 40 to 60 minutes. The altitudes in the table and the graph illustrate this. Explain why we didn't bother to include negative values along either axis when drawing the rectangular coordinate system for the altitude graph. What would it mean if the graph ever has a height below the x-axis? Negatives don't make sense on either axis. We cannot have a negative amount of time and height below the x-axis would mean the plane went underground. Okay, now we come here to problem 15. It says when we plot points that correspond to pairs of data on a coordinate system, we call the result a scatter diagram or a scatter plot. According to taxifarefinder.com, a cab ride from the airport in Las Vegas will cost you an initial charge of $5.10 plus $2.60 per mile. Use this information to fill in the rest of the table describing the total cost for various distances. Then create a scatter diagram using the distance as x coordinate and the cost as the y coordinate. Make sure you label a scale on each axis. Okay, now we need to finish up this chart here. We go from 510 to 770, which is $2.60, and $7.70 to 1030 is $2.60. So we know we're going to keep on adding $2.60. So it's $12.90, $15.50, and also $18.10. Okay, now we want to graph this. So if we look here, we add a distance in miles. It only goes from 0 to 5. So we could label these numbers as 0 to 5. And we can actually add in 6 for the extra value here. Now if we look at the cab fare, it goes from $5.10 all the way up to $18.10. Now if we count how many values we have here to put numbers, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places. So we could go by twos. So it'd be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And we're well within the range that we have here. Now we want to graph this. We start off at 0. 0 is $5.10. It's a little bit, it's almost the exact middle of between $4 and $6. Then 2, well then 1 we add $7.70, which means it's closer to 8. 2. I don't know why I want to skip over the numbers. So 2 goes up to $10.30 to be a little bit above 10. And then 3 would be $12.90, which would be close to the middle between 12 and 14. Then 4 would be $15.50, which would be a little bit above the middle between 14 and 16. And then finally 5 would be $18.10, so it would be a little bit above 18. Now if we connect these points, we draw an arrowhead because we know if we keep on going for that distance, it will cost even more money. All right, now, the next thing, we go down here to 16. What do you notice about the pattern that the points on your scatter diagram are making? Use that observation about a pattern to connect the points, drawing a graph that represents the cost of a cab ride based on distance. It's increasing at a steady rate. Steady rate of $2.60. So the points line up very well. Okay, now we move on to the next page. Actually, we move on to page 140. It says, we'll return to our cab ride graph in a bit, but first let's talk about drawing graphs in general. What temperature is this thermometer displaying? Okay, now, if you look at this thermometer, it has no numbers on it. So, I will put, I have no idea. Because without any numbers, how will we know? No type of labeling on this graph. Okay, now 18. Explain why the thermometer is pretty much useless. The marks on the thermometer are not labeled. What are the coordinates of the point drawn on the graph? Another one, I have no idea. The only thing that we know without a shadow of a doubt is basically the origin. That's it, but there's no other labels on this graph. So, explain why the graph is pretty much useless. There is no scale labeled on the axis. Okay, now that take care of the first part of section 2.3. Now we're going to move on to the last part of 2.3, and this is going to require us to use the calculator. So, we come here to page 141. It says, now it's time to refer back to the table and graph on page 138. The point where any graph crosses the y-axis is called the y-intercept for the graph. Write the coordinate of the y-intercept for the graph that you drew. More importantly, what information does the y-intercept represent? Okay, now, for some reason, this does not have the graph that we used on page 138. So what I'm going to do here, I'm going to bring back the graph to 138 here. This is the graph we were using. So they asked us for the y-intercept. The y-intercept is when x is 0. So distance was our x value. So our y-intercept would be 0, 5, 10. Now, it asks us to explain what this represents. This is the flat fee for the cab ride before adding any mileage. Charges. So basically, as soon as you sit in a cab, you got to pay them $5.10, and that is your y-intercept. And then after that, as you travel, you'll start paying the $2.60 for every mile that you travel after that. Okay, now for number 2. How much more will you pay for a 3-mile ride than a 2-mile ride? Okay, so now looking back at this table, a 2-mile ride is $10.30. A 3-mile ride is $12.90. So we'll put $12.90 minus $10.30. So that would give us $2.60, which is our rate of change. Number 3, how much more will you pay for a 5-mile ride than a 2-mile ride? Explain why that makes sense based on your answer to question 2. Okay, so the 5-mile ride is $18.10. The 2-mile ride is $10.30. So that would leave us $7.80. There's a 3-mile difference. Now this makes sense. It makes sense that 3 extra miles cost 3 times as much as 1 extra mile. Now back in problem 2, that was only 1 extra mile. This is 3 extra miles. So if we take the $2.60 and multiply it by 3, that gives us $7.80, which is the difference here. So it does make sense. Okay, now we go here to number 4. It says pick any 2 points on the graph that you drew and subtract the second coordinates. Then divide the result by the difference of the first coordinates for those same points. What does the result represent about the cab ride? Okay, so they told us to pick any 2 points. I would pick 2 and $10.30, and then 5 and $18.10. So they asked us basically to take the y values, which is the 2 second points, and subtract them from each other. So it'd be $18.10 minus $10.30. Take the second value minus the first value. Then we would do that with the x values. The first value, the second value minus the first value. So now when we subtract this gives us $7.80 over 3, which is equal to $2.60 per mile. So it says, what does the result represent about the cab ride? Okay, so what it represents is every extra mile costs $2.60. That's what it represents. Okay, now we need to move on to the next page. And we come here to problem number 5. It says, estimate the distance of a $16 cab ride. You could use either the table or the graph, but make sure you explain how you got your answer. Okay, so now we have to go back again to page 138 chart. The chart and the graph. Now it tells us to estimate the distance of a $16 cab ride. Okay, now, this is what we could do. If you look at the graph, I think it would be better to go to the graph. If you look at the graph here, it's actually a little bit past the distance of 4 miles. Just slightly past that. So, we could say the height of the graph is $16, just a little past x equals 4. So it would be a little over 4 miles. Now we're asked to estimate the cost of a 2.5 mile cab ride. Again, explain how you got your answer. Now, look down here at the bottom. 2.5 would be about here because it's going to be in between 2 and 3. So if we go up, it almost hits 12 exactly. It looks like it hit 12 exactly, but it is slightly different. So we could say again, halfway between x equals 2 and x equals 3, the height of the graph is about 12. So it will cost about $12. Now, move on to problem number 7. We know that the cost of the cab ride is going up by $2.60 for each extra mile. So how much would you pay strictly for mileage if the ride is 10 miles? Ignore the $5.10 you pay just for the privilege of getting into the cab. So basically, you would take the $2.60 and multiply it by 10. So that would be $26 because they told us to disregard the initial fee of just getting in the cab. Okay, number 8. How much would you pay strictly for mileage if the ride is X miles? Refer to question 7 if you need help. If you're really desperate, ask your professor. Just kidding. That should never require desperation. Okay, so now, basically what happens if we want to use X miles is $2.60 for every mile. So it's per mile. So it'd be $2.60 times X. Okay, so now we go to number 9. Now the key question, given that the initial fee is $5.10, and on top of that you pay for the mileage as described in question 8, write an equation that describes the cost of a cab ride, Y, in terms of the number of miles driven, X. So we would have Y is equal to, we know we would have $2.60 times the miles, but we have to add on the initial fee of $5.10. Now if you look at this here, this looks like Y equals mx plus b, which is slope-intercept form, which we would get to a little later. Okay, now, number 10. It says, how could you use your equation to check your estimate of the distance of a $16 cab ride? Do it. So basically, if it's a $16 cab ride, that will replace Y from problem number 9. So we would have Y equals $2.60 X plus $5.10. We would substitute in $16 for Y. Now, typically when I substitute, I put it in parentheses to signify substitution. So now we would subtract $5.10 on both sides. So on the left side, we would be left with $10.90 is equal to $2.60 X. So I'm going to write that over here to give myself more space. 1090 is equal to 2.60x. We divide each side by 2.60. And then x will be approximately 4.2 miles. Now number 11. How could you use your equation to check your estimate of the cost of a 2.5 mile cab ride? Now remember, this is the distance, so this would be our x value that we would substitute in. So we would have y is equal to 2.60x plus $5.10. So y is equal to 2.60 times 2.5 plus $5.10. Now, when we multiply this out, we'll take 2.6 times 2.5, and that would give us $6.50 plus $5.10. So y is equal to 1160. Okay, now we move on to problem number 12. There's a very useful lesson to be learned from questions 8 and 9. The $2.60 that it costs for each mile is the rate of change of your cost as the number of miles increases. And we know that a constant rate of change for some quantity represents the slope of a line when you graph that quantity. The $5.10 is the amount you will pay just for starting the cab ride. So 0 miles correspond to $5.10, and a 0.05.10 would be on the graph describing total cost. In fact, it would be the y-intercept. The equation describing the cost can be written y equals 2.6x plus 5.10, where x is the number of miles driven. Notice that the coefficient of x, which is the number x is multiplied by, is the slope of the line. Also, the constant term, which is the term without a variable, is the second coordinate of the y-intercept. Okay, conclusion. When a line has a slope m and the second coordinate of its y-intercept is the number b, then the equation of that line is y equals mx plus b. Okay, now, we basically proved that when we went through the previous problems from 8, 9, 10, and 11. Okay, now, number 12. A small business had just 12 employees when they opened their doors, but have been adding employees at a rate of 4 per month since then. Write a linear equation that describes the number of employees in terms of the number of months after the company was founded. Okay, so now they tell us we started off with 12 employees. So we know it'll be y equals, and they tell us that it was steady growth of 4 per month. So it'll be y equals 4 times x, and x will represent months, plus the 12 employees we started with. So if we want to write that out, it'll say where x is the number of months, and y is the number of employees. Now we have problem 13. It says use a graphing calculator to create both a table of values and a graph of the equation you wrote in question 12. The technology boxes on page 144 will walk you through the process. Okay, so now let's take a look at the technology boxes on page 144. Now if we look here, it tells us to press the y equal key to get the equation editor screen. Enter the formula you want to find values for using xt and so on. And then press second in window, and then press second in graph. Now, what I am going to do here, I'm going to go through each of these steps with problem 13. So, you press y equals, we will have basically 2.6, well actually no, we had a different equation. For problem 12 we will have 4x plus 12. Now that would be our equation. Now we're told here to go to second and window. Now we want to make sure that everything is on auto. So we have the table start. It has table start at 9. Let's do it at 0 instead of 9 if you have something different for the table start. Okay, so now the next thing we would do, we would go and we would press second, then graph. Now if you look here, if you move your arrow over from 0, we would get 12. And then here we have 1 for x, 16 for y, and so on. Now the reason why I moved over here is because sometimes your answer will have a decimal, and it typically will not show it in the y area unless you highlight the number. So basically, this is what we have. So now, basically we're done here. So we're done with section 2.3.